two long straight parallel wires are 2 meters apart, perpendicular to the plane of the paper, which is shown in the diagram. So we have a wire A and a wire B. The wire A carries a current of 9.6 amperes directed into the plane of the paper. The wire B carries a current such that the magnetic field of induction at the point P at a distance 10 by 11 meter from the wire B is 0. Find the magnitude and direction of the current in B, the magnitude of the magnetic field of induction at the point S, the force per unit length on the wire B. So for solving this problem, we will be using these working formula. So the magnetic field due to infinitely large wire is written as mu naught I upon 2 pi r. So we can rearrange the term to write this equation in this way as well, mu naught upon 4 pi into 2I by r. So we do this kind of a modification just to make sure that from mu naught, that is 4 pi into 10 to the power minus 7, we can directly cancel 4 pi. So we write equation in this fashion as well. And the value of force per unit length can be written as mu naught I1 I2 upon 2 pi r, where I1 I2 are the current in the long straight wires and r is the perpendicular distance between the two wires. So this is these are the two working formula which we will be using to solve this particular problem. So let us begin by first of all finding out the direction of magnetic field due to the current carrying wire in A. So since the current is carried in the inward direction, which is designated by cross over here, so I can say if we place our right hand thumb into the screen at point A, then the right hand palm will be directing us in this direction. So I am calling it as PM. So it will be directing us in this direction. So now in order to nullify the result of this magnetic field, it is important that the wire B must be carrying current in the upward direction so as to cancel the magnetic field due to A at P, and hence I am calling it as maybe it will produce a PQ magnetic field in this direction whose vector is represented by PQ vector. So if I start solving it out, so let us begin by calculation of magnetic field at P. So we are finding out magnetic field at P. So the first thing which we are doing is we are calculating magnetic field due to A. So due to A, we write it as mu naught upon 4 pi twice of current in A upon distance AP. So this is current in A and distance AP. So if I put the value, I can write it as mu naught upon 4 pi twice of current in A is 9.6 and the distance is 2 plus 10 by 11. So this is the value of magnetic field over here due to A. Now what we are doing is we will be calculating magnetic field due to B, which is opposite to the direction of the magnetic field which is produced by A at point P. So for B, I am writing it as mu naught upon 4 pi twice of current in B upon distance, which is 10 by 11. So now from both these equations, I can say for the magnetic field to be 0 at point P, it is necessary that magnetic field due to A must be cancelled out magnetic field due to B. So we can solve it out like this. So mu naught upon 4 pi term is common, 2 is common. So I can write it as 9.6 upon 2 plus 10 by 11 is equal to IB upon 10 by 11. So we obtain equation like this, and from here we obtain that the current flowing in the wire B is equal to 3 ampere and it is coming out of the plane of the screen. So IB is equal to 3 ampere. Now let us move back to this diagram. So in this diagram, the next question that is asked is the magnitude of the magnetic field of induction at the point S. So if we consider the dimensions So I can say that the dimensions are of an of a right angle triangle. So if the dimensions is of a right angle triangle, and we can clearly find out that angle ASB is equal to 90 degree. So it is a Pythagoras triplet, and angle ASB is equal to 90 degree. So for this particular part, we can write it as SA square plus SB square is equal to AB square. So it is clear from this triangle that it is a right angle triangle. So if we calculate magnetic field due to A at S, then it will be directed from S to B. So I can say that it will be directed from S to B like this. S to B. It is magnetic field due to A. So I am writing it as BSA. Magnetic field at a point S due to A. And magnetic field due to B at S will be directed from S to A, and both the direction is determined using Maxwell's right hand rule. So I am writing it as BSB, magnetic field at S due to B. So these two are perpendicular to each other. So if we do our necessary calculation over here, so I can say that we are solving the next part. So magnetic field at S due to A can be written as mu naught upon 4 pi twice of current in A by the distance, that is RSA. So we can write this as mu naught upon 4 pi twice of 9.6 upon the distance, which is equal to 1.6, and the direction we have already discussed, directed from S to B. Now we are calculating magnetic field at S due to B. So we write it as mu naught upon 4 pi twice of current in B upon RSB. So if we do this, we write it as mu naught upon 4 pi. So twice of the current, that is 3 ampere, upon the distance, which is equal to 1.2. And the direction is already discussed by us. It is directed from S to A. Now since both these magnetic field are perpendicular to each other, so I say that BSA and BSB are perpendicular to each other, and hence I can write the net magnetic field can be written as mu naught upon 4 pi, and then we will square the term and add them, that is 9.6 upon 0.8 whole square plus 3 upon 0.6 whole square. So we are basically doing vector addition, root over a square plus b square. Since the term mu naught upon 4 pi was common to both, we took it out, and on calculation we obtain a value equal to 1.3 multiplied by 10 to the power minus 6 Tesla. So magnetic field at a point S is 1.3 into 10 to the power minus 6 Tesla. Now in the next part, the question is asking us to calculate the force per unit length on the wire B. So for this part, we are saying that the force per unit length on the wire B, that is the third part. So I already specified the working formula, that force per unit length is written as mu naught I1 I2 upon 2 pi r. So if we do the calculation, we can write it as, so I am writing it as 10 to the power minus 7 into 2 into 9.6 into 3 by 2. So I have modified this expression by multiplying 2 on both sides. So from 4 pi we can cancel out mu naught and obtain 10 to the power minus 7, and on solving we obtain it as 28.8 into 10 to the power minus 7 Newton per meter. And it is important to mention over here that the force will be repulsive in nature, because they are carrying current in the opposite direction. So the force is of repulsive nature.